Okay, so I'm supposed to speak about the GW method. So the GW is a many-body perturbation theory. So one normally starts from some non-interacting Hamiltonian, like for example LDA. That's what we usually do in practice. And then we add self-energy corrections on top of these non-interacting Hamiltonian. So we work to first order in the screen interactions. So let me first show you some this original paper. It's a famous paper by Hedin from 1965. If you read the abstract, you will find that some interesting statement at the end of the paper. It says that there is not much new in principle in this paper. So, and then the emphasis is on the development of a numerically manageable approximation scheme. So I guess this is in 1965. So if you write something like this now try to submit to PRIL or something, it will be completely rejected immediately, I guess. So just want to give you some impression about this method that has been used quite a lot. So it's been increasingly used actually in recent years. It started actually already in around the middle of 1980, where we have first calculations of silicon using this method, and then it started to grow. So it looks a little bit like the global stock exchange before the collapse of the Lehman Brothers. Yeah. Perfect. So let me first show you some results that you get when you apply this scheme to real materials. So the emphasis here is on real materials. It's a method that allows you to do calculations entirely from first principles. There is no Hubbard U, there is no J or anything like this. You just take a Hamiltonian and calculate the self-energy. So this is a nice collection of semiconductors and insulators. They are well-known semiconductors and insulators. So most of them are not kind of strongly correlated materials that you've been hearing about. This is some just band insulators or band semiconductors. So if you look at the comparison with the experiment, so the experiment is supposed to lie on this straight line here. And this is the red one is the LVA, and the blue circles are the GW. So you can see a very systematic underestimation of the band gaps. And if you do GW, then it's based on LVA here. So I think this is just a one-shot calculation. You get a much better agreement with experiment. So the agreement is not just a matter of a qualitative agreement, but we are talking about very precise quantitative agreement here. So approximately the error is about 0.1 eV. So you can get accuracy to about 0.1 eV when you calculate the band gaps in these systems. So these are mainly SP systems. Yeah?
So if you look at the three, diamond, SRO, and aluminum nitride.
Yeah.
You see that there is a trend of it's up, down, and up. And GW also has the same trend, up, down, and up.
Yeah, it seems so, yeah.
So is that, so GW does just a quantitative correction, or is there a qualitative change in some physics there?
I guess this is partly due to the oxide that you have this problem. Like also in the zinc oxide, you have this problem. Diamond, I think it's not so bad. Here you get a good agreement here. but here,
let's say
yes.
for zinc selenide and copper gold.
Yeah.
So
So
maybe
you
the
have a
question
D
is,
electrons in the system. Yeah.
does it depend on the starting point, because your starting point is some energy you calculate?
Yeah. Yeah, it can be. So actually, there has been also self-consistent calculations. It's called the quasi-particles self-consistent calculations, where you improve the starting point using knowledge of the self-energy. And then you get the better results. So actually, you tend to overestimate the gap a little bit, but in general, it's better than the one shot. Yeah, I will speak about it later, self-consistency. Yeah? Sorry? Nothing. It's just separating the different materials. So here the experiment is supposed to be on the straight line. So this is the error of the LDA, and this is the error of the GW. Otherwise, it has no particular meaning. So you can think of this as the exact band gap. Yeah? So that is for SP systems. And I just show another one here to show how accurate it is. So this is a graphene. I just took this picture from this paper, not so, it's about 5 years ago. So if we calculate the Fermi energy, so this is basically just the slope of the band at the Fermi level. You know, this graphene has a well-known this cone structure at the Fermi level, so it's a point here. And you find that the LDA underestimates the Fermi velocity, but the GW gives a rather accurate result for this system. I think so. Yeah. Yeah, but then this is for free graphene. Yes. Oh, I see. Yeah, I see. I'm not so sure about this because I have not read the paper carefully. I just look at the plot the results. Okay. So here is also comparisons for molecules. I think they're looking at the ionization potentials for a collection of 32 molecules, kind of standard molecules that are used in quantum chemistry. So again, here you see quite a good agreement between the experiment and the GW. So these are the blue one are the Hartree-Fock. As you might expect, there is no screening in Hartree-Fock, so the ionization potential is too big. And when you include the effects of screening, you get a reduction in the ionization potential. So this I just want to illustrate the quality of the GW approximations. So as I said before, the GW approximation is generally good for SP systems, but not good when you have a strongly correlated system. So when you go to the 3D and the 4F systems, you start seeing problems. So these are the D block here and the F block. So for this, so for the S and P blocks, GW works well. So here, actually, it is not so bad. We have done the same calculations for nickel. This is one of the 3D transition metals. It's very old calculations. And we look at the quasi-particle band structure, comparison with experiment. So the experiment is the solid line. LDA is the dot line, and the GW is the dotted. So you could see that LDA overestimates the bandwidth. And here, the quasi-particle, the GW quasi-particle energy is actually quite good in comparison with experiment. So even for the 3D systems, but we start seeing some problems. So for example, the exchange splitting still too large. So this is the same exchange splitting as in LDA, compared to just about twice the value of the experiment. So somehow the GW cannot handle spin dependence. There is no spin dependence in the self-energy. There is a spin dependence that comes mainly from the Green's function, but not from the correlation, not in the W. So when we go to a 4F system, so then we see a real problem with the GW. So this is a well-known alpha to gamma phase transition in cerium. So basically they have the same structure, FCC structure, but one has a larger volume than the other. And this is the experimental spectral functions, the green one. And one see that as we go from the alpha to the gamma, one see a kind of drastic reductions of the quasi-particle peak around the Fermi level. So now if you try to do this system with GW, and you see that there is essentially hardly any changes when we go from the alpha to the gamma. So you can see that this is the blue curve is the projections on the F states. These are GW calculations. So you see when we go from the alpha to the gamma, we see there is no reduction. So it is not so surprising because we start from LDA band structure, which has essentially the same density of states here. And so we have perturbations on top of the LDA. Since the starting points are almost the same, then we don't expect a drastic change in the final result. But this illustrates the problem with the GW. So it doesn't get the right physics, so to speak. So on the other hand, if you do DMFT, LDA plus DMFT results, this experiment over the two phases, alpha and the gamma. So DMFT is quite capable of describing the correct reductions of the quasi-particle peak at the Fermi level. So with regards to strongly correlated systems, GW could be a good starting point, a background for many-body calculations in these correlated systems. So the picture I have is that when you start from the atomic limit, like Antoine described yesterday, DMFT is a suitable suitable method for describing systems with strong correlations. You start from the atomic limit, and then you take into account the hopping to the surrounding materials and the systems. On the other hand, GW starts from the electron gas picture. So you start from the band structure picture of the electron gas and takes into account correlations by means of screening. So you have the W here is the screen interaction. So real materials is somewhere here in between these two. So if you have a strongly correlated materials, then DMFT is a good method to use. And if you have a band insulator, for example, then GW is a good method to use. So it depends a bit on what you want to do. So for example, you don't do silicon using dynamical mean field theory. So it's not a good starting point to do silicon, you see, because the states are pretty delocalized. So in that case, one would like to use GW. So ideally then perhaps is to combine these two schemes, GW plus DMFT, And this is, I think, what Silke will speak about tomorrow and on Friday. So this is just a sketch of the photo emission experiment, because we are talking about band structure. So what we measure here is the binding energy of electron in the solids. So basically, we have a light coming in, and an electron is kicked out from the sample. So we measure the kinetic energy of the electrons, and from the conservation of energy, we can deduce the binding energy of the electron, which is just the difference between the incoming photon energy and the measured kinetic energy. So in the reality, it is not so simple like this. It's more complicated, but just schematically, it is basically like that. So, this the spectral functions of the photo emission experiment can be compared with the spectral functions that we get from Green's function. I think Vijay has already described this thing, so I just go through this quickly. So this is an exact expression for the Green's function, where one has in the denominator we have excitation energies of the n+1 and n-1 system, and this is precisely what is measured in the photo emission experiment. So we can make a comparison between the spectra measured in the photo emission experiment and the imaginary part of the Green's functions. So there is actually an important ingredient missing when we do the calculations, namely the matrix elements, in fact, that we have not taken into account when we make this comparison with the imaginary part of the Green's functions. That is often neglected, but can be important in determining the intensity of the spectra. So here I make a comparison between the Kohn-Sham equation that we get from density functional theory and the quasi-particle equations. So here we have the exchange correlation potential on top of the Hartree potential in density functional theory. And these eigenvalues, as we have already heard many times, do not have a clear physical meaning, with the exceptions of the highest occupied energy, which corresponds to the chemical potential. So the correct way of calculating the quasi-particle energies is by solving these quasi-particle equations. So more properly is one should use equations for the Green's function and look at the peaks in the imaginary part of the self-energy. But to a good approximation, one could also solve these equations, the quasi-particle equations. So now this self-energy is non-local and it's a function of the energy. So unlike DMFT, the self-energy in the GW approximation is non-local, meaning that it has a components, interside components. So we take into account all the non-local components of the self-energy.
How do you get this quasi-particle equation?
So this quasi-particle equation you get by writing the Green's function. So the equation, you start from the equation for the Green's function. So you have a Green's function instead of the wave function. And then you write it in this form. And you will find that this quasi-particle wave function here is essentially this quantity here. This quantity, what I call F and H. So what we need is the self-energy here. So I just follow what Hedin wrote in his paper. So this is maybe the last review article he wrote. So the GW approximation extends the well-known Hartree-Fock approximation for the self-energy exchange potential by replacing the bare Coulomb potential by the dynamically screened potential W. So we can just think of the GW approximation as a kind of generalization of the Hartree-Fock approximation, where we replace the bare interaction V by screen interaction W. Now it's not so simple like that, because when we use bare interaction, when we use the screen interaction W instead of V, this screen interaction actually is a function of frequency. So in addition to in addition to screen exchange, we will get some other term coming from the frequency dependence of the W. So let me see. So basically, what we do in the Green's function language is that we write the exchange as a product of the Green's function and the bare interaction. And if we use a non-interacting Green's function, then we will find this well-known expression. It's the exchange potential. It's non-local. So in GW, basically what we do is just replace this V with a screen interaction. So we have a same diagram, except that the interaction is now screen. And that's basically it. So if you are not too fussy about how to derive this expression from more formal things, then this is basically what we have. So this is a little bit heuristic, but we can go to yeah. So epsilon here is the ratio between the total potential and the applied potential. So I found some old animation that I did quite many years ago to describe a little bit about screening. So let's see if it still works here. I have a photon coming in. So I have a hole here. So I have a photon coming in, kicking out an electron, and I have a hole which is then screened by the surrounding electron. So we have a hole screened by the surrounding electron. So one can think of this as a kind of a quasi-particle. It's not a very precise picture, but approximately like this. So this hole, so this system is no longer in an eigenstate because we disturb the system, putting a hole. And so this the hole eventually will decay in time. So that's why you have a lifetime for the quasi-particle. And also that you get a screening effect. The interaction between the hole and another electron will be screened by these electrons here. So you have a situation like this. So let me, since I think I have time, so let me try to derive the GW approximation in a more formal way. So let me try to do this more slowly. So I start from the Green's functions in the interaction representation. So we did this before when we talked about the constraint RPA, when we derived the response function. So we want to use the same technique to derive the self-energy. So actually, it's a very nice technique to obtain the self-energy without going through complications with the Wick's theorem or with a complicated time ordering. So here we just do functional derivatives. Yes. So we start from the Green's functions in this interaction picture. So let me explain what this means. So psi 0. So psi 0 is the exact ground state without the perturbation. So the idea is to apply perturbation phi to the system, and this perturbation is a tool. We don't actually apply this physically. So it's just a tool, mathematical tool for obtaining response functions or the response of the Green's function with respect to this field. And we can show that the response of the Green's function with respect to this field is related to the two-particle Green's functions. And we know that the self-energy is actually just a two-particle Green's function. So in that way, we can make a connection between the self-energy and the response of the Green's function with respect to the field. It's the first-order response function. So this quantity S here is essentially just a time development operator. So this was from -infinity to infinity in time. And we can write the Green's function in this way. So the field operator here in the interaction picture is independent of the field. So this is an important point, because we are going to take a functional derivative of this quantity with respect to the applied field. So there is no dependent of the field on the there is no dependent of the field operator on the external field, the external perturbation. So this is the field operator in the interaction picture. It's just a unitary transformation of the Schrödinger operator, field operator. So when we then take functional derivative, all we need to do is just the functional derivative of this time development operator with respect to the external field. So when we do that, we will bring down the density operator. So we just get this expression here. And the position of this density operator can be after or before this S operator, because this consists of two field operators, so you can just interchange without changing sign. So now we start with the equation of motion. So this you can get from looking at the equation of motion of the field operators. So you can derive this from the Heisenberg equation of motion for the field operators. And in doing so, one find that the Coulomb interactions, which consists of four field operators, will generate two-particle Green's functions. And as you probably already know, that if you try to write equations for the two-particle Green's functions, then you will end up with three-particle Green's function and so on. So you want to truncate the hierarchy of the equations to get an equation just for the one-particle Green's functions. So this two-particle Green's function is defined in this way. So it consists of 4 field operators. So one create or annihilate two particles instead of just one in this case. So to truncate this hierarchy of equations, one defined a mass operator in this way. So this is the definitions of the mass operator M. So it is. So this 2-particle Green's function is then written in terms of the 1-particle Green's function with this self-energy or the mass operator. So schematically, I can then invert this equation to get the explicit expression for the mass operator. So now we can show that that this 2-particle Green's function can be expressed in terms of the derivative, first derivative of the Green's function with respect to the external field. So I just take the functional derivative of this Green's function with respect to the field. So as we said before, the field operators do not depend on the phi, so we only need to worry about the derivative with respect to this S here. So then there will be 2 terms. First term here comes from the numerator, so I'm just taking the derivative with respect to S, and that gives me the S and times the density operator. And there will be another term coming from the denominator. So we have the original term here times the derivative of this. That gives me that term. So it is quite simple. You take functional derivative. But this quantity here is just the 2-particle Green's function, or can be written in terms of 2-particle Green's functions. So it is quantity here. So this 3 or 3 plus come from the density. And this quantity here is just the original definition of the Green's function times the density. So we can write the 2-particle Green's function in terms of the derivative of the Green's function with respect to the field. Now we could rewrite this in a form that allows us to generate an equation for the self-energy. So by using this identity, so it's just an identity. If you start from the fact that g by g minus 1 is equal to 1, and you take the functional derivative, that gives me an expression for this thing in terms of the inverse of the Green's function with respect to the field. So if I come back to the expression for the mass operator, so I just write this in a schematic way, then we could replace the 2-particle Green's functions by this quantity here. So the g disappears because I have g minus 1 here. And then I have this term coming from that one. Yeah. But this first term here is just the Hartree potential. So just V Hartree. And then we are left with this quantity here. So now we use the identity in these expressions, and we get that term. So now we are ready to calculate the the self-energy. So the self-energy in our definition is usually defined without the Hartree potential. We subtract the Hartree potential. So this just contains the effects of exchange and correlation. So this Hartree potential is removed from the mass operator. So it looks a little bit funny here. Okay, so I just rewrite the full expression. I just put back the variables from the previous expression. So this is given by this integral here. So now we could do a little bit of manipulations to rewrite the derivative with respect to field, not with respect to the original external field, but with respect to the total field. So we define the total field to be the Hartree field plus the external field. So we do that, we just use the chain rule. So this, I'm just using a chain rule here. So this is the definition of the inverse dielectric function. So then this V times the inverse dielectric function gives me the screen interaction. So now we write everything in terms of the total field instead of the original field. So in this way, the self-energy then has the following expression. So instead of the original bare interaction, we have the screen interaction. Now this quantity here is usually called the vertex function. So it's a 3-point vertex function. And so the formal expression for the self-energy is given by this quantity here. So the question is then how we get a concrete expression for this self-energy. And we can do that by using the equation of motion. So we start from the equation of motion. So we can calculate this vertex by taking functional derivative of the g to the minus 1 with respect to the total field. So the total field is just this thing here, the phi plus the Vr3. So that gives me 1. And then we get the contribution from the self-energy. So in the GW approximation, we neglect this contribution from the self-energy, set it to 0. So the vertex then is just 1, or just delta functions, product of delta functions. So this gives them the GW approximation. So we can continue doing this manipulation with the functional derivatives and set up kind of closed equations involving the self-energy and the screen interactions. And if we do that, probably I would not go through all these details, but I have it in the slides, so you can read it later if you like. So we'll have this on the website. So if you do the same kind of manipulations, you end up with a closed set of equations. So it's sometimes called the Hedin's equations. So there is an equations for the vertex. This is just the Dyson's equations. And we have the self-energy that we derived before. And we have a similar expression for the polarization. So we have a GG times the vertex functions. So in the random phase approximation, we set the the vertex function to 1. So then we get the product of two Green's functions. So let's see how it works. So this is actually not an integral equations, but rather it's an iterative equations. So you cannot actually just invert these equations, but rather you have to iterate. So we do that. So let's start from self-energy that is 0, because we don't know what self-energy is, so we just put it to 0. So then this gives us Green's functions that corresponds to the R3 Green's functions, because we don't have any exchange and correlations. So when we do that, this is 0, so then we just end up with the products of delta functions, and they can calculate the polarizations. And then this gives us the RPA equations for the screen interaction. And if we use the same vertex here, then we get the GW approximation. So that's how it works. Now one could continue, go back here, and now we have a self-energy, and take the functional derivative with respect to the Green's function, so that will give us a vertex corrections. Then put this the vertex here. It will give a new polarizations and a new screen interactions, and then we get a new self-energy, and so. So actually, you can show that if you do that, you get exactly the same diagrammatic expansions that you would do when you use Wick's theorem. So you get exactly the same diagrams. So the difference is that in Wick's theorem, usually you do the diagrams order by order, but here you get the diagrams in different orders. So you generate several diagrams with different numbers of interactions, but if you do the full calculations, you get the same diagrams. So as you can see, we don't worry about diagrams here. Actually, we just take sigma by dg. Okay, so if I have this expression, for example, then I just take the first term will be just give me the w. Yeah. So then you get another term. Then you get another term coming from the w. You can include it if you want. Exactly. Yeah. That generates a series. Yeah. So of course, we do not want to do this kind of iterations, because already after GW, it's hard to go beyond this by taking functional derivatives. So maybe you could still calculate this by fixing the W, and so that actually gives you the vertex that one uses in the polarizations when you want to calculate excitons. That actually gives the ladder diagrams in the excitons. So actually, if you calculate the vertex with the W, you get the P would be like this from this one here, and then if you continue, you will generate the P like this, like that, and so on. So basically, we just take this one and this one in GW, and if you want to do excitons, you should include this one also and this. So let me come over here. Let me spend some time, a little bit, the explicit expressions for the self-energy. So we start from this the self-energy, this is GW, and we can write this in the frequency space with the Fourier transform. So this is a product in time space, so then we get a convolution. So if we use either this one or this one here for the non-interacting case, we can do some analytic calculations for the frequency integral. And so it's not difficult to do. So we have basically just a contour integral. So if we just multiply the Green's function and the screen interaction, so the screen interaction can also be written in the spectral representations. So actually I made a little mistake here. So this is the correlation part of the screen interactions without the Coulomb interaction. So this should be omega W minus the bare interaction. So if you do that, you get it's a nice expression for the self-energy. It can be split into two parts. That's called the screen exchange. So it's called screen exchange because it has exactly the same form as a normal exchange operator, but now it's a screen interactions, not the bare interactions. And then in addition, we have a contribution that is usually called a Coulomb hole, or correlation hole, that involves not only occupied states, but all states, because we now have to sum over all states. So we can understand a little bit about this GW approximations if we make the following approximations. So this screen interactions has a collective excitations, which is the plasmon excitations. It's typically very high in energy compared to the quasi-particle energy. So to good approximation, so actually this is not a very good approximation, but anyway we will do this. So we set this to 0, and if we do that, we can then do these summations, become an identity, and we get the following expressions. So this first term here has a simple interpretation. So this is just the screen exchange, exchange between spins, electrons of equal spin, but with a screen interactions instead of a bare interaction. And the Coulomb hole has a more interesting interpretation. So this is the screening potential coming from the screening charge, and these are just the quasi-particle at R prime. So one can think of this as an interaction energy, as a Coulomb interaction energy between the quasi-particle and the screening charge. And the factor of 1/2 can be interpreted as an adiabatic switching. So you start from 0 to this value, so then you get a factor of 1/2 this process. So the picture is relatively simple. You have a screen exchange, and then you have an additional contribution coming from the interaction between the hole, quasi-particle hole, and the screening charge. That's the physics of GW. So here I would like to do a little exercise to show that GW actually describes correctly the quasi-particle energy for relatively weakly correlated systems. So this, I take a Polaroid model. I have just one level. You can think of it as a core electron, and you have a plasmon, it's a boson here, and then you have a coupling between the electron and the plasmon. So this is exactly the same Hamiltonian that you get in the electron-phonon Hamiltonian. Yeah. So we can then do a little exercise to calculate the self-energy within the GW approximations. So this is exactly the same mathematics as you do when you study electron-phonon coupling. So you write just the Green's function like this, and then we calculate the plasmon, the corresponding Green's function for the plasmon. There's a plasmon energy here. And then we just calculate the self-energy. It's just a product of these two with this coupling constant square. So this is you can do very easily. You get an analytic expression for the self-energy. So now we can calculate the quasi-particle energy. This is how we can calculate the quasi-particle energy. So this is the original energy plus the self-energy corrections. And we usually make a linear expansion of the self-energy. So we calculate the self-energy at the original one particle energy plus corrections from the derivative. And this can be rewritten in terms of the z factor. So well-known expressions. So if we calculate this, we get the following expressions. So the exact result is given by this. So I don't derive the exact result. It's just been, you can calculate the exact solution to this Hamiltonian. And you find that the exact result is given by this epsilon plus g squared minus plasmon energy. So GW gives this result here. So you can see that if the coupling constant is relatively small compared to the plasmon energy, then this is a good approximation compared to the exact result. So this is of course a little bit qualitative because the model is very much too simple. But in any case, we can understand a little bit why the GW approximation gives good quasi-particle energies. So also here is if the coupling to the bosonic excitation becomes too strong, then this is not a good approximation anymore. Now the one interesting thing is that if we calculate if we set the z factor to 1, so if we don't renormalize the quasi-particle weight, we find that this gives the exact result. So this is maybe related to the question of self-consistency that I will come back later. So here I took this picture from the book of Ashcroft and Mermin. So I would like to describe the application of GW to the electron gas. So here we have the free electron band, and if we do Hartree-Fock, you can do this analytically. You find that the occupied bandwidth is approximately twice the free electron bandwidth. And as you know, the Hartree-Fock has a problem that when you calculate the density of states, there is a logarithmic singularity, and it gives you 0 density of states here. Now we know from experiments on the alkalis that a free electron approximation is quite a good it's a good approximation to the photoemission spectra. So this suggests that if we include correlations, then it will cancel the effects of this band broadening. So if we include correlations on top of the Hartree-Fock, then we get back essentially the free electron band. So this is what happens when we do GW for electron gas. So we start from the free electron, and if we do just a one-shot GW, we get a band narrowing of the occupied state. part of the band. So the screening reduces the Hartree-Fock bandwidth a lot. Yeah. So it essentially brings back the Hartree-Fock band to the free electron band. So there's also two other plots here from the self-consistency. I will come back to this later. It has been used to calculate the total energy. Okay, so for the so if you do total energy, if you don't include interaction, then the free electron total energy is of course very wrong. Yeah? So you should not compare that. It's very wrong. But the interesting thing is that if you calculate the total energy with a self-consistent GW, you get a very good agreement with the Quantum Monte Carlo result. But I'm going a little bit ahead here. But if you look at this plot here, this is the fully self-consistent result. It's not good at all because we know that the bandwidth should be narrowed. But self-consistent GW actually widens the bandwidth. Yeah? So that is not a good result. But the total energy turns out to be very accurate. Yeah?
So the self-consistent GW, is that a conserving approximation?
Yeah, it's a conserving approximation. Yeah. So I just want to show you how the self-energy looks like. So this is the result from the one-shot calculations, the imaginary part of the self-energy. And this is the real part of the self-energy. This is just the Kremes-Kronig. There is a Kremes-Kronig relation between the real and imaginary part. And self-consistency then tends to soften this sharp peak. So let me skip that. So this is a comparison between the Hartree-Fock and GW band gaps. So this is just to illustrate that the screening reduces the Hartree-Fock gap. So the yellow one here is the GW, and these are the Hartree-Fock. So again, you've already seen that you get good agreement with the experiment when you include corrections. This is, I think, the hybrid functional. Yeah. It's not so good. Oh, that I do not know. It's very good. Yeah. Yeah. But you know, this functional is there's a lot of fiddling in the.
That's why I'm asking, is it with the same value of light?
Yeah, that I do not know. But,
This comparison can make, for example, by taking some system and applying pressure and measuring the band gap, and also comparing that with the experimental band gap measured under pressure. Is that under pressure?
Yeah.
Suppose you change the lattice structure,
Yeah.
the band gap will change a little bit.
yeah,
So has that been checked out?
for the GW. There are some early calculations by Rex Godby that he studied this dependence of the band gap as a function of pressure. And it turns out to be quite good. Yeah. So the GW method has been applied also to surface. So this is to illustrate that if you do LDA, you find that the exchange correlation energy, the exchange correlation potential decays exponentially. So there's a surface here. So that is of course not correct. It should go like 1 upon r of the image charge. And GW on the other hand gives you the correct behavior. So now I'm coming back to self-consistency. So as I said before, self-consistent GW unfortunately gives not a good result here because it widens the bandwidth, whereas we know from experiment that it should narrow the bandwidth. So maybe we can try to understand a little bit why this is so. So let me first show the, yeah.
Why do you think that it may not be other effects? For example, including phonons gives you enhanced, also gives you band error.
Yeah, but
On top of the GW, but the GW actually is right, but if you include that's dynamics, you will.
yeah, but I mean for electron gas.
Electron gas, who does experiments on the electron gas?
No, but I mean in the alkalis. Yeah, but I do not think that the energy is comparable to the electronic energy. It should be much smaller.
But here you're showing only for electron gas, I guess.
Yeah.
So you can vary it increases.
Yeah. Yes.
No, but he has done a model calculation.
Hey, no, but
What to compare with?
the question is, nobody really measures the free electron gas.
No,
or
definitely.
the
That
electron
is-
gas. So why should we know that the electron gas really has a band error?
Yeah, that is of course true. But I mean, if you neglect the phonon, at least you can make this reasoning that it should be narrowed.
What RS is this done?
This is done at RS4. Yeah. So this is the effect of self-consistency on the spectral functions. So this is that dash is the one shot at the quasi-particle peak here, and then there's this plasmon satellite. But it turns out that the plasmon satellite in GW is usually too high in energy. So this is the separation between this and this is too large. This is not a 1 plasmon energy, but typically about 1.3 or 1.5 plasmon energy. So actually, self-consistency seems to improve the positions of the plasmon satellite because it reduces. But as I said before, the bandwidth seems to be poor. Yeah. Give the right result. So this is I have already shown. So to do self-consistent calculations, you kind of soften the peaks in the imaginary part of the self-energy. So this is maybe not so surprising because when you use renormalized Green's function, then your Green's function is no longer peaks. You get certain energies. You get a broadening coming from the lifetime. So let me try to understand what happens when we do self-consistent GW. So I just consider a two-level model. So I have two states, one below and one above the Fermi level. So I can write the Green's function, and it's very easy. So let's say that after self-consistency, we get a renormalized G like this. Actually, it is not so clear that self-consistency will give this kind of spectral functions. There may be more peaks, but let's just assume that I only have one additional peak below and above. Let's say located at some energy, plasmon energy here. So what happens is that the quasi-particle weight Z is reduced from 1 here to Z, and so the rest of the weight is in the satellite, in the plasmon satellites, 1 minus Z. So I can recalculate, I can calculate the renormalized Green's functions, and now it has 4 terms, 2 for the occupied, this one here, and 2 for the unoccupied. So it's a very simple model. I just want to understand what happens when we renormalize the Green's function. So I can then just calculate the polarizations, which is just a product of two Green's functions. So then we see that the polarization function now has 4 terms, and the largest is this one here, because this thing involves the omega p, which is much larger compared to the epsilon 1 or epsilon 0. So these terms are relatively small compared to the first term. So if we just consider the first term and look at the static value, then we find that this is approximately given by this quantity here. So if we compare this with what we get for P0, we find that there is no renormalization factor in the P0. So this means that the P0 is reduced by this Z factor, and Z is less than 1. So the screening has been reduced in this case. So one can then understand that if we use a renormalized Green's function, the screen interaction tends to be bigger than the one that you get if you use non-interacting Green's function. So the conclusion is that self-consistency tends to reduce the screening because of the presence of this factor, the Z factor here. So this is consistent with what we had before. So we look at this result here. So self-consistency reduces the screening. So that means that we are going towards Hartree-Fock because you reduce the screening. So then that tends to widen the bandwidth. That can understand. You can also understand that self-consistency should increase the band gap because the band gap is essentially determined by the strength of the screen interaction. So as a result of this reduction in the screening, we get an increase in the bandwidth and increase in the band gap. So self-consistency also broadens the spectral functions, and it decreases the plasmon energy. Now, as Tanushree asked, this is the numbers for the total energy obtained from the fully self-consistent GW calculations.
So the velocity singularity is not there.
It's not there. No, it's not there. But already in the one-shot GW, that singularity disappears. Yeah. So this is the results for the total energy from self-consistent GW. So for just 2 RS values, 2 and 4, and this is the Quantum Monte Carlo data. So it's surprisingly very good, and it's not entirely clear why this should be the case. So we just know that it is good.
It's self-consistent GW.
It's self-consistent GW.
How GW, one-shot GW compared to this is very bad? Or?
It is tend to be higher.
Okay.
So it's not good actually. So the no, so these are just electron gas, so you just use plane waves. Yeah.
But the previous results you showed some are from plane wave.
So which results you have in mind?
Like the band gap you showed.
The band gap. Yeah. Yeah. So this the band gap.
Yeah, I think the Stuttgart one was with the
Okay, so that is with the full potential LMTO. Yeah.
I mean, it also depends on the basis set.
Yeah, it can depend on the basis set, but this is more a question of it's a more technical issue and a theoretical issue. Yeah.
That's true.
It's true. Yeah, but it's true that the result can depend on which basis you use. So this is technical problems.
I noticed that the GW self-consistent GW result is lower than all the separately
Yeah,
DMC.
yeah, because there is no variational principle in
I
here.
understand, but does it give you some clue as to how to improve the wave function? So it's a fixed node Monte Carlo.
Yeah, I think so. Yeah, this is separately older.
So does it give you some idea of what you should do to the wave function to get better?
Yeah, that's a good question. But the thing is, this is based on the Green's function approach, yeah? And this is Monte Carlo. So I don't know how you improve this, because we don't have much information about the wave functions from the GW calculations. We work in the Green's functions, so we don't have any wave functions. So I don't know if we can deduce anything about the nodes of the wave functions. So let me show some results also for the molecules. So here a self-consistent GW seems to work better. So my understanding is that in molecules the screening is less important, and so this renormalization effects is also less important compared to what you have in solids. And here we have a better agreement with the experiment. So all of these are based on the calculations. It's a bit difficult to understand things at the quantitative level as to why it works like this and why it works like that. Qualitatively we could understand, but when it comes to quantitative comparison, then we don't have much choices other than doing some calculations and see how it works. So then this comes to the questions of what to do with GW. So it is not nice to do just a one-shot GW calculation starting from some non-interacting Hamiltonian, usually the LDA, because this gives you some arbitrariness in the starting point. You can start with LDA, and there are many different kinds of functionals. You can use hybrid functionals, or you can use PBE or whatever you have, and you might get different results depending on where you start. So the idea is then to do some kind of self-consistent calculations, but restricting the self-consistency at the quasi-particle level. So we do not use the renormalized Green's functions, but just use the quasi-particle energies at the quasi-particle level. We do self-consistency. So actually we know the quasi-particle equations. It is given by this. But if we calculate the wave functions, then they are no longer orthogonal, because first of all, this self-energy is dependent on the energy. Yeah. So if we use different energies, then these wave functions do not correspond to the same Hamiltonian, changes in energy. So then in general, these wave functions are not orthogonal. And also, this quantity is not Hermitian. It has an imaginary part, which is not Hermitian. Only the real part is Hermitian. So the first step is to neglect the imaginary part of the self-energy and the energy dependence of the real part of the self-energy. So in this way, we get a Hamiltonian, which is Hermitian. And this is a kind of somewhat ad hoc way of finding some approximate self-energy. So first we neglect the imaginary part, so we get self-energy of this form. You can write this self-energy in terms of the block states. This is just a mathematical expansion. And this matrix elements of the self-energy is then taken to be some kind of average of the energies of the self-energies at two energies, n and n prime here, for a given k. So this is done in this paper here. So this provides then a kind of recipe for performing self-consistent calculations at the quasi-particle level. Yeah. So the idea is then to use this approximate self-energy here, solve the quasi-particle equation. So we get a new set of wave functions and energies. And from this, you can calculate a new Green's function and calculate a new screen interaction and get a new self-energy. And then use this again, like until you get self-consistency. So alternatively, one could also solve the quasi-particle equations as it is. So you just solve this. You just solve this. You can find the energies. And then one tries to orthogonalize the quasi-particle wave functions using the Levdine's orthogonalization procedure. So basically, one like to minimize these differences subject to orthonormalizations of psi k n. So this can be done. There is a well-defined procedure for doing this. So this is the results when you do one-shot GW. So this is the picture I showed in the very beginning. And I compare this result with a self-consistent quasi-particle self-consistent GW. So as you can see here, the self-consistent GW quasi-particle at the quasi-particle level improves things quite a bit, actually. So it tends to overestimate the band gaps. So still not perfect, but at least it improves quite a lot of cases where a one-shot GW is not good enough. So this is especially important because the particle self-consistent GW is especially important when the wave function changes from the LDA. So, for example, if you do vanadium dioxide, it turns out that the wave function changes quite a lot when you do these self-consistent calculations. And this is important in opening up the gap. So this is the nickel oxide. There's always this controversy between this nickel oxide in the Slater picture and then in the Mott picture. But anyway, you can do calculations for with this method. If you do this self-consistent calculations, the band gap opens up, although it turns out to be somewhat too large. It is, so the experimental band gap is about 4 eV. And here we find something more like 6 eV. So I'm talking about the separation between this EG band and this band and this band here. So this band is pushed up here. And also this is an S band, which is pushed up here. So now the separation is more like 6 eV. So that's about 2 eV larger. So again, we see in this kind of strongly correlated system, so GW has problems even when you do self-consistent calculations. Still have problems. And another interesting thing is that in these calculations, the top of the valence band is still of D character. It's not of oxygen D character. So it is still a Mott insulator rather than the charge transfer insulator. Like, so you would like to have in the charts in the the charge transfer gap, you would like to have the oxygen band to be in between the 2D bands.
So does it mean the position of oxygen P bands is still wrong with GW?
Yeah, if you believe that the P band is up here, then it's wrong.
Discussion about the position of oxygen P
And the
and
D.
DA gives it wrong.
Yeah.
But then GW also gives it.
Yeah, it still gives it's still wrong in this case. At least if you believe that the oxygen should be up here. Yeah. But actually, I don't know if it is already determined in a convincing way that the top of the valence band must be D, there must be oxygen or not. This I do not know. Yeah. If it is a charge transfer, then it should be up here. Yeah. But GW definitely does not show any tendency to move it up. So actually, it is yeah.
How much is the maybe it's up there? How much is the
Yeah, you can.
oxygen bands
Yeah.
with respect to LDA?
So it's almost the same actually. So
Yeah,
there
it's
is
not so much.
there is hardly any shift.
So the oxygen renormalization with oxygen P bands is not so much.
It's not so much. No. It's almost the same as in the LDA.
For your triangles in your triangles in your graph are experiments, I guess.
Yeah, these are
So
experiments.
question, what kind of experiments?
That is photo emission by the Shen group in Stanford. Yeah. So you can see also that the experiment band here, it's very difficult to read really. So only the oxygen P band has a well-defined dispersion. But here you can see that it's, I don't know what kind of bands you have here. Just bunch of points, but without any clear dispersion. So that in a way indicates that the system may not have a well-defined quasi-particle peaks or something because of the strong correlations. But anyway, this is what we get when we do GW.
So what is shown here
Yeah.
is triangles are results from the angle result potential.
This
That's
one
the
here.
angle result potential.
Yeah.
So if the zero is the final energy,
Hmm.
that's pretty flat, right?
Yeah.
But if I go to the XPS,
This one here.
yeah, are the energies matched? Then I should see certain peaks
Yeah.
there.
Yeah. So these are the peak here.
Yeah, but little should be.
Yeah, but I mean, there's also a lot of weight here.
That's right.
It's a bit difficult to see from here because there are a lot of, it is just part of the Brion zone, right? So you have to sum over all the Brion zones. So the controversy is still there. It's not finished yet. Band structure people, GW people, would like to think of it as a Slater insulator. Well, you can describe it here, but maybe it is the wrong physics. I tend to believe it's the wrong physics, but don't know. So here's another example for gadolinium doing self-consistent GW. So this is the LDA. Let me see if I have that time. Okay, I can have another 5 minutes or so. So in gadolinium is at the middle of the 4F series. So half of the spin channel is completely filled, and the other half is empty. So this is completely filled. This is the F4F band here, and this is the 4F band of the minority spin. So it's completely empty. Now, experimentally, it's like this. So these are supposed to be from the F states. So you see that the position of the occupied 4F state is much lower compared to LDA. as you might expect. But also the unoccupied part is pushed up here. It's very much high. So what happens when we do self-consistent GW? Actually, it is not so bad. You can get the correct description for the occupied parts. But the unoccupied state here, the 4F states, not very clear, but somewhere here, is much higher compared to the experiment. So again, it indicates that even when you do self-consistent calculations like this, GW still has problem. So this is a very big error. So because of the have a localized states, things no longer look like electron gas in the system. So apparently correlations play an important role in this system. So actually it could be interesting to do DMFT calculations for this. I don't know if it has been done, if you can get the correct separations of the 4F states. Now LDA plus U has been done. You can get the right peak here, but then that's because you adjust the U. So yeah, so this is another example of so actually it's nice view too. So if you just do a one-shot GW, you actually do not open up a gap, but you do when you do self-consistent calculation. So this indicates that that the change in the wave functions is important. Yeah, I know. Yeah, I think it is the same. You get a yeah.
That's in the Rutan.
Sorry.
In the Rutan phase.
Yeah, yeah. In the Rutan phase. Yeah. And this is another result for. And again, I want to show that the failure of GW. This is, I think I have shown this before in the conference. So this is for strontium vanadate. We want to look at the band here. This is T2G band. If you do self-consistent calculations, again with the GW, you still have problems with the band narrowing. So there is not enough band narrowing even if you do self-consistent calculations. But one good thing is that we got a better positions of the oxygen band. So I believe LDA is too high, so there is a lowering by about half an EV when you do GW.
So do we understand why for nickel oxide there was not a strong denormalization, but for strontium we do see some effect on the oxygen?
Yeah. That's a good question. It's not so easy to see why there's a narrowing here.
Your EP minus ET, the charge transfer gap for nickel oxide is much smaller compared to that in strontium vanadium.
I mean, the charge transfer gap in the case of nickel oxide, I suppose it should be between this one and this one.
No, there you also have Hawking effect. It's not a right range estimate. You also have the Hawking effect.
Yeah.
Their energy by C, because nickel is a late transition metal.
Yeah.
I would expect the EP minus EP will be smaller.
Mm-hmm. Okay.
Should I repeat the question or we just forget about it? Because we are close, very close to the.
Okay, we can discuss it later. It's a little bit technical. Anyway, my time is a little bit up, so let me just mention some problems with the GW. So already at the SP materials, we have problems. And so if you do self-consistent calculation, band gaps tend to be overestimated, and also plasma satellites. But in particular, there is some serious problems when you apply this to strongly correlated systems. So for example, too large band gap in nickel oxide and the gadolinium, there are no lower and upper Hubbard bands, or they tend to be too high in energy if you calculate the satellites. And certainly cannot describe the Mount Hubbard metal insulator transition. So let me just conclude here. So this is something that Zilke, I think, will speak about. So this gives a motivation to combine this GW with dynamical mean field theory. Okay, so let me just summarize this. Yeah. So GW is accurate for SP systems, but problems when you apply to strongly correlated system. But we hope that it provides a good starting point from anybody calculations. So let me stop here.
Are there questions and comments from students? Not quite students.
Yeah.
Actually, for insulating or semiconducting systems, the acceptor level position is always a problem for LDA or other kind of calculations. Now, acceptor level position, I just want some comment from you. How does GW compares with HSE06 for hybrid functional and other things? How does GW compares the acceptable level positions?
So I think GW should be able to describe this acceptor level correctly. I don't know how it is compared though, with the functional that you mentioned. So I know that this functional is designed to describe such problems.
Because whatever you have shown, those two problems, nickel oxide and other strontium vanadate, one is metallic, another is insulating. So for the insulator part, it's not comparing so well, but I will say that strontium vanadate is better compare. It's a better comparison. Oxygen levels and other things, for strontium vanadate, it's a closer comparison. But how does it compares with HSE06 in two cases?
I don't know if it has been done for this material. It's hybrid functional.
Hybrid functional.
Yeah. So my guess is that.
Insulating system, it should give better result, but not for metallic, of course. Yeah.
So my guess is that nothing happens with the bandwidth. So it remains in the LDA.
It's just altogether for the band gap, not so much for the dispersion.
Right.
Oh, thank you.
I think that sort of connects to what I asked and nobody could hear is why the oxygen P positions were so different for nickel oxide. And there is a denormalization. I don't know whether is that the reason. I don't know.
Yeah, that certainly is a difference, but I don't know how to see this. I should see through.
Can I just? So what you just mentioned, right, that the starting point of GW is an electron gas.
Yeah.
Right, and then you build over it. On the contrary, if you work with theories like DMFT, starting point is an atomic picture, then you build. So I would get most insulators should be, the starting point atomic level is a much relevant description rather than starting from an electron gas.
Yeah.
Right, and possibly that can be one of the reasons.
The oxygen P level position. Anyway, we can discuss.
Yeah.
Are there further questions from the students? Well, if not, let's thank Hedin again.
Okay.
And we break for tea.